Okay, so we're going to look at some questions looking at the photoelectric effect and also looking more generally at how wave theory changed into sort of a more particle type theory and giving us the idea of wave-particle duality. So that's the focus of these questions. So let's get started. So we've got example A with UV photons with a certain energy, and we've got some photons of another energy, and they both have enough energy to cause electrons, so they both have photon energy greater than the work function of each of the materials. Okay, so what are the frequency and wavelength associated with the radiation in examples A and B? So let's do the frequency first of all. So we're going to use the equation E equals HF, rearranged, and then we just need to plug our numbers in to give us what the frequencies are. Fairly straightforward. Once we have the frequency, what we can do is we can use the wave equation, and then because we know the frequency now, we can then work out what the wavelength of each of the radiations is. Okay, so question 2, explain why the electron absorbs more energy than it needs to escape from the metal. So the key here is this idea of one-to-one interaction. So either a photon has enough energy to emit the electron and the electron absorbs all of the photon's energy, or the photon doesn't have enough energy and the electron will not interact with that photon. Those are your two options. Nothing else is possible. So in this case, you have to absorb all the energy, so that's why it will do that, because you have to. Okay, so question 3, write an expression for the potential energy of an electron of charge E due to a potential difference Vs, which I think is going to lead us on to some stopping potential stuff. So the general equation we're using is the work done by a potential difference is the charge times the potential difference. So the potential energy of an electron at a given potential difference is going to be the charge of an electron, which is E, times whatever the potential difference is, in this case Vs, which is going to be our stopping potential, I think. Okay, so during an experiment, zinc was irradiated with photons in example A. The stopping potential, or the stopping voltage, was found to be 0.88 volts. Calculate the work function for zinc. So the general strategy here is the stopping potential allows us to work out the maximum kinetic energy of the electrons. Photon energy will then allow us to work out the work function. So the first thing I'm going to do is work out the maximum kinetic energy using the stopping potential. And then I'm going to rearrange Einstein's conservation of energy model to give us the work function, and that's our answer here. So the work function of calcium is 4.64 times 10 to the minus 19. What is the minimum frequency of radiation that will release electrons from the surface of calcium? Okay, so the work function is related to the threshold frequency by the Planck's constant here. So because we know the work function, we can just rearrange this equation, plug the numbers in, and that will tell us what the threshold frequency is. So the work function and the threshold frequency are inextricably linked together. So if we know one, we can calculate what the other is. So a photocell is illuminated with ultraviolet light of wavelength 328 nanometers, and photoelectrons are emitted. The potential difference across the photocell is varied and the current is monitored. A graph of current against potential difference is shown in the diagram. Explain why the current has a maximum value. Okay. So just in terms of what we can see on the diagram, we can see that we've got a stopping potential of -2. So that would tell us about the maximum kinetic energy. And you can see is as you decrease the potential of the plate, we get a higher and higher current. And then we end up with a fixed current at the end once we are no longer opposing the emission of electrons with our stopping potential. So the reason the current has the maximum value is because it's determined by the intensity of the radiation. Because remember, once the photon energy is greater than the work function, one photon causes one electron to be emitted. So that's the key here. Again, we've got this one-to-one interaction. So the current is limited by the intensity of the radiation. Okay, so we want us to determine in electron volts the maximum energy which photoelectrons are emitted. So we're going to use the stopping potential from the graph, which you could see is minus 2 volts. So I'm going to calculate the maximum kinetic energy using that 2 and the potential difference, and then divide by the number of joules that 1 electron volt is to give us 2 electron volts. So you can see actually I could have just read this straight off the graph that it's 2 electron volts. If the stopping potential is given in volts, that actually gives us the maximum energy in electron volts. So there's actually a simpler way of doing it. Gives the energy of photons from the ultraviolet lamp. So what we're going to do is use the wavelength to calculate this. So we know Planck's constant, we know the speed of light, we know the wavelength, so we can calculate what the energy is. Again, it wants it in electron volts, so we use the same conversion factor, and we get 3.79 electron volts. Determine the work function of the photocell. Well, it's going to be the difference between those two numbers, essentially. So we get 1.79 electron volts. So back on the original diagram, sketch an additional graph to show the effect of using the same ultraviolet light, but on a lower intensity or a lower brightness, if you like. So it's going to look like this. So we're using the same material, so it's going to have we're using the same energy of photons, so we're going to have the same maximum kinetic energy and therefore the same stopping potential. But what's going to happen is our lower intensity is going to limit the maximum current that we can achieve. So that's how we determine the shape of this graph. Explain why a particle model of an electron is unable to explain electron diffraction. Well, so the particle model would predict that when electrons are incident on a double slit, 2 maxima should be detected, because particles occupy a single point in space. They'll either go through one slit or they'll go through the other one. So we should get 2 maxima, essentially. But when you actually do the experiment, it produces an interference pattern. So we produce a lot more than 2 lines. And that indicates that the slits have acted as 2 coherent wave sources. So the electrons must be acting as waves. So calculate the de Broglie wavelength of an electron traveling at 6.22 times 10 to the 7. So there's a simple equation to make this conversion. Plug your numbers in. We know the mass of an electron. You can get it from our data sheet, and that gives us the de Broglie wavelength. In an experiment to test the ideas of Louis de Broglie, a stream of electrons was aimed at a thin film of carbon atoms. The pattern of the electrons formed on the screen after the electrons have passed through the film is illustrated by the diagram. So what you can see here is the maxima and minima forming. So we can see we've got a maximum in the middle, we've got a maximum a bit further out, and a maximum further out, and a very low intensity in the bands in between. So this is a sort of an interference pattern on multiple dimensions that we're making here. Okay, so describe how the results changed our understanding of the electron. So the pattern shows an interference pattern, and that means what must have happened is we've got constructive and destructive interference of electrons. And that means that electrons were able to behave both like particles, but also like waves, because interference or superposition is a wave property. So essentially what this indicated is they could behave like both particles and waves. Calculate the de Broglie wavelength with this speed. So same deal, but with a different speed, gives us our wavelength. Okay, so we've got a magnesium plate in a vacuated glass container, and it's being illuminated with ultraviolet radiation, also known as a photocell quite often. Another metal plate at the opposite end, and 2 plates are connected through a microammeter to a variable DC supply. The polarity of the DC supply can be reversed. Okay. State the name of the effect that causes electrons to be emitted. That would be the photoelectric effect. Calculate the photon energy of the ultraviolet radiation in joules. So we're just going to use this equation here with our wavelength of the radiation, and that gives us our energy. To turn that into electron volts, we're just going to divide that by the 1.60 times 10 to the minus 19 joules. That is what 1 electron volt is. That gives us our electron volts. We've now got the work function. So to calculate the maximum energy, we're just going to find the difference between our two energies. It gives us 1.28 electron volts. Sketch on the graph to show how the current might vary with the potential difference between the two metal plates. So we get a graph like this that we've seen in previous questions. If we apply a negative potential difference, we can stop emission occurring at what we call the stopping potential, and then we reach this limit of current, which is limited by the intensity of the radiation. If we add on another graph with a lower intensity but the same type of radiation or same wavelength, we get the same stopping potential but a lower maximum current. So this would be our stopping potential. We just calculated it in the previous question, so I think we should be labeling it on our graph because we are able to. Explain why the answer to E was so unexpected when the experiment was first performed. So let's talk about what was expected first of all. So wave theory, intensity is proportional to amplitude squared. So a dimmer, less intense light was expected to produce lower energy emissions. Okay, so if your incoming wave has less energy, we expect lower energy emissions. Kind of makes some logical sense there. But what happens is the energy of the emissions are not affected by the intensity, and we can see that by the fact the stopping potential is the same for both of the experiments. So all the intensity affected was actually the rate of emission. And that means that wave theory could not fully explain the behavior of light, and we needed to modify it to include a particle model as well, and that could enable us to explain the results because it predicts things like the one-to-one interaction, and it says that intensity is just the number of photons arriving per second. It doesn't actually affect the energy each photon has, which is why the energy of the emissions doesn't change. So that's how it changed it. So light of wavelength 470 nanometers strikes a thin film of an alkali metal. The work function of the metal is 2 times 10 to the minus 19 joules. Calculate the photon energy of a light of wavelength 470. Fairly straightforward, just using the equation we've used several times. Calculate the maximum energy of a photoelectron emitted from the metal surface. Well, we can use our conservation of energy model. If we do our photon energy minus the work function, that gives us our maximum energy. So light of wavelength 470 nanometers is used in a device called a Photomultiplier Tube. So just for your general information, these are used as part of things like gamma cameras, which are used with tracers that you use in medical imaging. They come up a lot in different medical devices as ways of detecting things like gamma rays and so on. Anyway, we've got a photomultiplier tube with 6 electrodes labelled 1 to 6. So light falls on a photocathode which emits photoelectrons using the photoelectric effect. These electrons are attracted to the electrode because it's a higher potential, so it's positively charged. And each electron causes the emission of 15 electrons, so the incoming electrons are actually causing ionization and emitting lots of electrons. Okay, so this process is repeated, which is why it's called a photomultiplier tube. You're increasing the number of the electrons, and the reason you're doing it is because if you produce a large enough number of electrons, that produces a detectable current at the other end. So the rate of emission is 4 per second, so we're emitting 4 electrons every second at the photocathode. Calculate the number of electrons leaving the 6th electrode. Well, if each one multiplies the number by 15, we need to do 4 times 15 to the power of 6, giving us 4.6 times 10 to the 7 electrons per second, which should hopefully give us a detectable current at the other end. Okay. Calculate the current arriving at the other side. So all we need to do is multiply it by the charge that each electron has, and that gives us our current in amps. Explain why the electrons arriving at the final electrode have more energy than the initial electrons. Well, they've had work done on them by the electric field. So the potential difference creates an electric field which is accelerating our electrons, and that increases the electrons' kinetic energy, and that's why they have more energy. And also we have many more electrons now which also have been accelerated, so we're going to have quite a lot more energy. So photomultiplier tubes, like the one shown in the diagram, can be used to make a night vision camera. Give suggestions why such a night vision camera can only give a black and white image, even though the incident light may have many different wavelengths. Well, the key here is the process in between this, the photoelectric effect and this acceleration process. So, any wavelength with sufficient energy will cause one electron emission regardless of its wavelength. So if it's got enough energy, it doesn't matter if it's like green, yellow, red, ultraviolet, whatever it is, it's only going to emit one electron. Okay, so we're losing information about the wavelength that's incoming. The next thing is that the work done by the electric fields is far greater than the emitted kinetic energy. So we can't really use the initial kinetic energy of the electrons to tell us anything, because that difference is negated by our accelerating potential differences, and then remembering that our electrons are colliding with lots of other electrons anyway, so we can't really get a good reading on what the energy of the emission is. So we've essentially lost the information of the wavelength that was incident. Okay, so in this whole process we've lost that information. So that means this machine is not going to be able to differentiate between different wavelengths. It'll just tell you whether there has been a wavelength above the threshold frequency or not, essentially. So the other thing is that the color of the emitted photons at the other end of this whole process is determined by the energy levels inside phosphor. It's not determined by the incident radiation. So again, that's going to mean we're not going to produce any useful output color, which is why we're only getting a black and white image. Which graph shows how the energy of a photon is related to its wavelength. Energy is inversely proportional to wavelength, so that gives us this one. In the photoelectric effect, the light incident on a metal surface causes electrons to be ejected from the surface. Which statement is correct? Electrons are ejected only if the wavelength is greater than some minimum value. No, it's if it's less than some minimum value. Remember, to get higher energy, we need shorter wavelengths, so that doesn't make sense. The de Broglie wavelength of ejected electrons is the same as the wavelength of incident of light. I've never heard of this rule, so I'm going to skip over that because that doesn't make a lot of sense to me. But I don't necessarily know that it's wrong, I've just never heard of it. The maximum energy of the electrons is independent of the intensity of the incident light. That is true. Energy is not tied to intensity. Maximum energy of the electrons is independent of the type of metal. No, different metals have different work functions, so that's not true. That is not independent. So I'm going to go with statement C. Atoms in a gas emit photons of light of energy 2.44 electron volts. What is the wavelength? So first we calculate what the photon energy is in joules, then we can plug it into our equation and we can see it's option B. Which statement about the photoelectric effect is correct? Any photoelectron current produced has a value that is dependent on the intensity of illumination. That sounds pretty good. Photoelectrons are not emitted when the light has a wavelength below a certain threshold. That's not true. Lower wavelength gives you higher photon energy, so it's the other way around. It would be above a certain threshold. Maximum photoelectron energy depends on light intensity. Note that it's independent. It has no effect on it at all. Work function is the energy of an electron that may just cause a photo emission from the metal surface. No, work function is the energy of the photon, not the electron. So we can see it is indeed option A. A laser emits light at a wavelength of 632 nanometers. It illuminates an area of 1 × 10⁻⁶ meters squared. The intensity is 1.5 milliwatts per meter squared. How many photons of the laser land on the paper each second? So first, let's calculate the energy of one photon using our equation. Then I'm going to calculate the total energy that arrives every second. So intensity times area gives us power. Power times time gives us energy. So this is the amount of energy that arrives in 1 second. And then using those two, we can work out how many photons arrive per second, which is clearly option A. Two sources of light, X and Y, have the same intensity, but X has a longer wavelength than Y. Both sources are shone onto a metal surface and cause the emission of photoelectrons. Which row is correct? So let's actually figure out what we know about these two. So if X has a longer wavelength, that must mean it has a lower photon energy. So that's the first thing that we can deduce. If they have the same intensity, that if X has a lower photon energy, that must mean it has a higher number of electrons per second than Y, so that we end up with the same intensity. So that's the two things we know. So if there are more photons per second for X, that must mean it's either A or B, because we're going to get more emissions from X every second. But Y has a higher photon energy, so it's going to give you a higher maximum kinetic energy, which is why it's option A. Okay, so we're given some information about the mass and speed of a football and a golf ball, and it wants the ratio of their de Broglie wavelengths. So the long way of doing this is to calculate each of their de Broglie wavelengths and then divide them to give you the ratio, which is clearly option A. The short way of doing this is you can see that the mass of the football is clearly 10 times bigger than the mass of the golf ball, but its speed is 1/3. And you can see that's going to tell us it's either A or C, because we're getting this ratio of 3/10 or 10/3. And then you have to figure out which way round they go, and that you can end up with option A. So there is a shorter way of doing it, but this way you definitely come out with the correct answer. So I'll use this one. What is the de Broglie wavelength of an electron that has an energy of 54 electron volts? So the first thing I'm going to do is work out what its kinetic energy is in joules. Then I'm going to work out what its velocity is using that kinetic energy and the mass of an electron. And then finally, you can plug that into the de Broglie equation to calculate what its wavelength is. And that clearly comes out as option C. So those are the stages that we would go through. Which graph shows the relationship between photon energy and wavelength? So photon energy is inversely proportional to wavelength, or another way of saying that is photon energy is directly proportional to 1/, the wavelength. So it's option B. Monochromatic light of wavelength 650 nanometers is incident on a clean potassium surface. The work function of potassium is 1.81 electron volts. What is the maximum velocity of the electrons emitted? So work function we can calculate using by converting to joules. Photon energy we can work using hc over lambda, and then we can find the maximum kinetic energy by defining the difference between those two, and finally we can rearrange the kinetic energy equation to find the velocity, which is clearly option B. In which piece of evidence about the photoelectric effect cannot be explained using a wave model? So increasing the intensity of illumination increases the rate at which electrons are ejected. The wave model can to a certain extent explain this, because if there's more energy incoming, either it can give the electrons more energy, or in the wave model you could give multiple electrons energy, so that can be explained. Shining ultraviolet radiation onto a zinc surface ejects electrons. Again, that doesn't really help us differentiate between the two. Shining visible light on potassium ejects electrons. Again, it doesn't differentiate between the particle and the wave theory, really. That there's a threshold frequency below which no electrons are ejected. It's this one here. So the wave model says any frequency or any wavelength should cause emission, just that lower energy ones take longer. But particle model is what predicts this threshold frequency. White light falls on a photoelectric surface, causing the release of photoelectrons, many of which are moving when released. Threshold frequency for this surface is 5.3 times 10 to the 14 Hz. So that's yellow light. So what that means is anything with a wavelength shorter than yellow will cause emission. Anything with a wavelength longer than yellow will not cause an emission. So which statement is correct? If a red filter is interposed, the number of photoelectrons released per second will decrease to 0. So if you have a red filter, that will only let through red light, and red light is not capable of causing an emission, so that seems like it's correct. If a violet filter is interposed, the number of photoelectrons released per second will increase. No, because if you put a violet filter, you'll filter out your yellows, oranges, which could cause emission as well, so that's not true. If the light is focused on a small patch, the electrons released will, on average, be moving more quickly. Nope. Focusing the light might emit more electrons in that region because there's more photons arriving in that region, but you're not changing the photon energies arriving, so you're not going to change the energy of emission. It takes a little while for enough energy to accumulate on the surface before any electrons are released. No, this isn't true. Emission happens instantaneously. Either a photon has enough energy or it doesn't. This was an aspect of the wave model of it. So clearly it's going to be option A. What is the energy of a photon of light wavelength 3.1 times 10 to the minus 7? Well, I've gone straight away for option A because it's the only one that's in the right order of magnitude to be possible. An electron volt is an incredibly small unit of energy. Anyway, these other ones just don't make sense to me. But if we actually work through the calculations, we can work out the energy, convert it to electron volts, and you see it is indeed option A. So electron momentum has corresponding de Broglie wavelength lambda. Which graph shows a relationship between lambda and p? Well, wavelength is inversely proportional to momentum, so it's going to be option A. Which graph shows how a maximum kinetic energy of electrons from a metal surface depends on the frequency of radiation absorbed? So the first thing is we should be seeing a threshold frequency, so there should be no emissions up to the point where you get a certain frequency and then we start getting emitted, and that's only shown by option B. All the other ones don't show a threshold frequency. Electrons are accelerated from rest through a potential difference V. How is the de Broglie wavelength related to V? So the first thing is the kinetic energy is directly proportional to the potential difference, because essentially the kinetic energy is determined by the work done by the electric field. Okay, and then that means, because kinetic energy is proportional to velocity squared, that means velocity squared is proportional to the potential difference. Moving forward, we know that wavelength is inversely proportional to velocity, which means wavelength squared is directly proportional to 1 over the potential difference, or another way of writing that would be what it says in D, that wavelength is inversely proportional to the square root of potential difference. Monochromatic light of wavelength 650 nanometers is incident on a clean potassium surface. Work function is 1.1 electron volts. What is the maximum velocity of emission? Those of you who are more eagle-eyed will have spotted this is actually a repeat of the earlier question, but let's show the solution anyway. So we can get the work function by converting the electron volts into joules. We can get photon energy using hc over lambda. That allows us to get the maximum kinetic energy, and then that allows us to get the maximum velocity of emission. Some of them will have velocity below this because they were deeper in the material, but this is the maximum possible velocity, and that completes this set of questions on the quantum physics.